VSEPR, valence shell electron pair repulsion theory, tells us about the shapes and bond angles of molecules and ions. Okay, and we'll do much more on this next year. When I say ions, I mean compound ions like nitrate and carbonate and whatnot. We'll come back to that. So compound ions. It's all about knowing where the positions of electron domains. So I'm going to define the electron domains as regions of electron density in the valence shell. And by valence shell, of course, I mean the outer shell. Okay, I mean the outer shell, valence shell, outer shell. Okay, and the electron domains can either be bonds, single, double, or triple bonds. Oops. Or there could be lone pairs. The other word for, or other way of saying lone pairs is what? Tell someone near you. Giving you a little clue. Okay, you can't remember. So non-bonding pairs of electrons. Okay, lone pairs are non-bonding pairs. They're the sort of things you get on water and ammonia, right? So our first set of molecules we'll look at are molecules with 4 electron domains. Okay, and as I said at the start, we're going to be really precise with the language we use. So I'm going to start off talking about methane, which is CH4, methane CH4. Now, really, with these, the best thing to do each time is to draw the Lewis structure. Okay, so you look at that, and we're looking at the shape around the carbon, the central atom. And so what we do is we count the number of electron domains, but we show the examiner, we know whether they're bonding domains or whether they're lone pairs. Okay, so we just count, so hopefully you can see here there's 4 bonding domains, or 4 bonds. Domain just means region, right? Regions of electron density, and no lone pairs on that carbon. Right, and so what we will see is that every time you've got 4 bonding domains and you've got no lone pairs, we get what we call a tetrahedral shape. And I'll draw that for you and justify it for you if I can, and I'll show you using a model in a sec as well. So, tetrahedral electron domain geometry. See how precise the language has to be. So it's a tetrahedral electron domain geometry. In other words, what that means is the electron domains are spread out as far away from each other as they can, and the way that we draw that, can you draw this exactly as I'm doing? So I'm drawing this in 3 dimensions now with a wedge coming towards me, and a wedge and a sort of dashed line going away from me. So it's narrow near the carbon and fat away from the carbon, those 2 lines. In order that the electron domains to move to positions of maximum separation or minimum repulsion. So get that all down and then drop your pen. Then I'll explain it for a little bit and then we'll move on to a few other examples. Okay, I'm not quite finished methane yet. Get all that down and drop your pens and we'll go from there. Right, so pairs of electrons are negatively charged, right? If negatively charged things don't like being near each other. They like to get away from each other as far as they can. And it just so happens that if you take something with 4 things around it, and it's a 3-dimensional structure, the positions where they can get as far away from each other as they can look like that. That's just these grey bonds they're getting as far away from each other as they can. And the picture that I've drawn, it's not going to work very well, it's something like that. So the 2 hydrogens, vertical one and one to the left, are in the plane of the paper. And the 2 other hydrogens, one's going behind and one's coming in front. It's sort of like that. Do you see how what that 3D picture looks like? We expect to be able to draw those 3D structures, and that'll help us next year as well when we do more difficult things. Okay? So you have to say exactly this language, that the electron domains are moving to positions of maximum separation and minimum repulsion. And that ends up with the bond angle, just as an outcome from the just basic geometry. It turns out that bond angle is 109.5 degrees, and I expect you to know that bond angle. And it's not just me, it's the exam board. I'm not just wanting it for my own sake. And all of the bond angles are the same as each other, and if you look at this, that makes sense. So bond angle for every hydrogen to each other hydrogen is 109.5. Okay. There are, in this molecule, no lone pairs. So the molecular geometry, in other words, the geometry around that carbon, is also tetrahedral. Okay? So whenever there's no lone pairs, the electron domain geometry and the bonding the molecular geometry are the same as each other. You'll see examples where that's not true in a minute, and I think that statement will make more sense when you've seen that. Okay? I'm going to move on. I'm just going to check I've not missed anything. I don't think I have. Right, good. So we're going to move on to another tetrahedral one, but I'm not going to spend as long on this one. The arguments for language will be exactly the same. The reason I quite like this example is that it's an ion. Right, so you just start to see that these exact same arguments apply to ions and neutral molecules. Okay, so ammonium. I'm not going to write it all out, but an ammonium ion, which is NH4+, would look like that. Tetrahedral, electron domain geometry, molecular geometry, everything. Yeah.
Oh, where's the molecular geometry?
Yeah, so it's the geometry around this carbon, referring. It'll make more sense when you've seen ones that aren't true. So ask me that again in a minute. But essentially, the molecular geometry is the geometry of the atoms around the carbon. Now, I'll just explain very briefly now that in a minute we'll have molecules that look like that, where there's a lone pair up here. So we'll call that electron domain geometry still tetrahedral, but the molecule itself, we ignore the lone pair and we give that a different shape name. Okay, that's all it is. Okay, but I'll get to that in a minute. All right. So ammonium, so tetrahedral. I'm going to call it, just for shorthand here, EDG and MG, molecular geometry, 4 electron domains, etc. We'll write out the answers fully with other examples. Okay. So I'm going to diverge from the slides a bit now because I don't want to do things in quite the same order. It's like the slides I'll share with you, that is, because I think it makes sense to do things in a slightly different way. Are you with me? Happy? Let's go. So another molecule that's got a tetrahedral electron domain geometry, or 4 pairs of electrons around the central atom, is ammonia. So ammonia, of course, is NH3, and if you were to draw a Lewis structure of NH3, which you did last lesson, it will look exactly like that. Okay, so you've got a lone pair now where there was a bond before. So I want to be consistent in what I said, so I'm just going to make sure I've written it the same way. So we've got 3 I'm really sorry. 3 bonding domains. It's got 3 bonds around the nitrogen. It's got 1 lone pair. So in total, there are 4 electron domains. So just like before, we've got tetrahedral. If I just write electron domain geometry, you kind of happy with that? Because I'm getting lazy. Yeah. Tetrahedral electron domain geometry. And then if you just write max sep min repulsion, exactly the same as before. But the molecule now, which I'll just quickly make, looks a bit different. So we haven't got a tetrahedral molecular geometry anymore. We've got what we call trigonal pyramidal, because we've lopped off one of the carbons, one of the hydrogens, but we've put a lone pair in its place. So let's just draw that. So we'll just write the name of it, which is trigonal for the fact there's 3 of them. So trigonal pyramidal, because it's like a pyramid. So it's like a triangular base pyramid. Yeah, pyramidal molecular geometry. And the way that you would draw that is just like the methane on the previous page, but the lone pair is up where that hydrogen once was. Now what do you think the bond angle would be then? Damien? Yeah.
109.
You'd think it would be, wouldn't you? That would make sense, wouldn't it? But it ain't. So every time there's a little rule of thumb that's worth kind of getting your head around is that every time there's a lone pair, everything gets squished together a little bit by about 2.5 degrees. Now the numbers aren't perfect, and you get given a range of allowed answers in your IB exams. But if you stick with the numbers that I give you, which are the ones that I was taught at school, they'll get you full marks. So if we just go with this, it's easy to remember. So it's 107 degrees for that bond angle there, approximately. And if you look it up for that particular molecule, it might be a little bit out from that. This is right, because VSEPR is only a model. Yeah.
Was ammonium also 109.5?
Ammonium was, and you'll see why in a minute. Okay. So ammonium, if you want to go back to ammonium on the previous page, also 109.5. Because it's tetrahedral metric geometry, they're all the same. Okay. All right. So why then is it pyramidal rather than trigonal pyramidal rather than tetrahedral? I'm sorry. Why is it 107 rather than 109.5? Well, the answer is exactly this language again. So lone pairs, or we should say lone pair to lone pair repulsion. Is greater than lone pair bonding pair repulsion. Repulsion, which is greater, I've messed it up, greater than bonding pair repulsion. I'll explain that in a sec. why would that be? This will probably need explaining. Right. The lone pairs, I'll try and draw it. I'm not very good at drawing this. I'll do it a little aside. If this goes wrong, we'll have a second go. If you imagine a covalent bond, I'm going to draw ammonia. Don't copy this yet because I might mess it up. But if you imagine the ammonia molecule I've just drawn, I'm going to mess it up. Those bonding regions are really kind of sausage-shaped regions of electron density, and we'll talk about that much more next year. Okay, it's kind of what they look like, and that's because this pair of electrons is pulled by the two nuclei. Right, that pair of electrons, those pairs of electrons are attracted to both the hydrogen and the nitrogen. So you end up with this kind of sausage-shaped region of electron density. They're not really just a pair of electrons sitting there. They spread out and they average out in that kind of space. Lone pairs are in much more spherical regions, and that's because they've got no second atom pulling electrons away from it. So you don't need to say any of this, I'm just trying to tell you to help you understand it. But lone pair regions tend to be a bit kind of like, like squat and fatter because there's not the second atom, whereas bonding domains are much thinner because they've been pulled out like a balloon that's been pulled sideways a little bit, okay? Pulled by both atoms. All you need to know is what I've told you here on the notes, that lone pair repulsion, which we haven't come to yet, is greater than lone pair bonding pair repulsion, which is this repulsion. That repulsion there is greater than bonding pair repulsion, which is greater than this one. So what happens is these electrons that are lone pairs are pushing down on all of these electron domains, squishing it a little bit closer together. So in this model, it's kind of squishing it like that, you see, by 2.5 degrees. Does that explanation make sense? If you can kind of give me a nod to see that you followed that kind of, right? But I told you what to say, and hopefully I've explained it in a way you can understand it too. Okay, all right with that? Makes sense? Bon. Right, move on. Let's do another example. Right, let's just finish off this sentence. So, because lone pair bonding pair repulsion is greater than bonding pair repulsion, bond angle, and it has to be the angle between two bonds. We don't count the bond. This is not a bond angle here. That's not a bond, so we don't look at that angle there. Oops. We're looking at the angle between bonds, not this angle here. This angle will be greater. So it's this angle here, that's 107. So bond angle is less than 109.5, okay, by about 2.5 degrees. Let's do another example. Let's do water, which we all know is H2O, and we all can draw a Lewis structure for. Well, some of us couldn't draw a Lewis structure of water in our recent test, unfortunately. Some of you thought hydrogen was in the middle, and they're one of them, and thought oxygens were either side of them, which is slightly depressing, but never mind. So that's what water kind of looks like up to this point. That's kind of the GCSE version of what water looks like. In reality, water looks like this. It's what we call a non-linear or bent shape, and I'll explain why using the language we need. And what do you reckon the bond angle is there, please, based on the logic that we've just used? What do you reckon? Tell someone near you what you reckon the bond angle would be? So 107, yeah, 107 take 2.5 is 104.5. If you said 105 in the exam, some of you might have done, you probably get the marks. But let's use what I've taught you. That will work nicely. Okay, and what we do is we go through the process again. We say two bonding domains, two lone pairs or two non-bonding pairs. But we've still got 4 electron domains. In total, And so the electron domain geometry is still tetrahedral. In order that the pairs of electrons move themselves into positions of maximum separation, or if you like, minimum repulsion. They try and get as far away from each other as they can, in other words, but you've got to use that language. But we say the shape of the molecule, the molecular geometry, is bent or non-linear. And you're expected to know all of this. So you can see how many, I think this is easy marks, right? If you get one of these molecules, you could get a mark for counting the electron domains, getting the right number of bonding and lone pairs, saying the shape of both the electron domains and the molecule, getting the bond angles right, and explaining it. You can see there's a heap of marks here. Relatively easy, I would argue, okay? And you would justify that again by saying the lone pair repulsion. So lone pair to lone pair repulsion is greater than lone pair bonding pair repulsion, which is greater than bonding pair repulsion. Right? And so again, that second lone pair is also squishing those together. And if I were to make water for you quickly, so you've used these molecules for years, but has anyone ever commented or noticed that the water had a particular shape and it wasn't just linear, had that sort of shape? Because the lone pairs that would be, well, you can't see it very well, if I hold it that way around, one lone pair would be this side and one would be this side, and they're squishing down, they're pushing those bonds closer to each other by a total of 5 degrees, okay? So we get that bent or non-linear shape. Okay, I need some more paper. Right, some other examples then. Again, there's quite a lot to learn here. That's the one thing that's tough, I suppose, about this little thing, this little topic. That's all the ones with 4 I can think of. Shall I do other examples? Might do with those for now and come back to other examples later. Right, so let's do ones with 3 electron domains. So the one that we'll use is boron trifluoride, which, remember what I've just showed you at the start of the lesson, BF3 is an example, like BCl3 or BH3. I told you you'd see them again, where they are exceptions to the octet rule. There's only 6 electrons in the outer shell. So that, with the Lewis structure, I should put the lone pairs on the fluorines. Though they're not involved in the shape, we should get the Lewis structure right, eh? So that's what that would be. And again, we go through the process, so we say that there's 3 bonding domains, 1 lone pair, and what am I doing? No lone pairs, and a total of 3 electron domains. In an exam, please write the words. And this shape, okay, if I can find, I'm not going to be able to find the right atom here. Never mind. This is what we call a trigonal planar. Trigonal, again 3, trigonal, but it's planar. Planar just means flat, completely flat. Electron domain geometry. And then, again, don't forget to say max set and in repulsion. So the electrons move to positions of maximum separation, trigonal planar, or and sorry, for the molecular geometry as well, is also trig planar, right? Because there's no lone pairs. And what that looks like is it's just dead simple. It's just completely flat. So if you take 360 and divide it by 3, so circles are 360s. What do you reckon the bond angles are around this, please? Huh? Yeah, it's going to be 120, right? It has to be. So it's 120 bond angle there. Okay. And though this is sounding very simple and straightforward now, hopefully, I can tell you that my year 13, so we've just done a bit more on some of this stuff, practicing it, are finding this kind of difficult to remember. What's up?
Just have a question. Why do all the lone pairs on the fluorine, like atoms, aren't involved in the lone pair count?
Because it's the effect of these electron domains on each other. I mean, these other lone pairs are really nowhere near enough to each other to have an effect. And anyway, if they did, on that, there will be some effect on them. And you know, all that stuff is explored. If you go beyond key stage 5, there are interactions across molecules, but the interaction between, say, this fluorine and this fluorine lone pairs will be minor compared to the effect of these lone pairs. Sorry, these bonding pairs down here, just because of the location, just because of, you know, they can't get any closer to each other, right? So there's kind of pushing each other like that. Yeah.
Do you ever have to do electron domain geometry for molecules that have like 2 in the middle? So if all the ones you've done is like 1 in the centre, but if you have like alkane.
Yeah, we'll come to that. Yeah, we'll come to that. What have I missed out? Yeah, that one's that one. So this applies also, just to make a note, this applies to BH3. It applies to BCl3. Well, we'll do that now, since you asked. We'll do this, a more difficult example of this. And this is an important rule then that you've highlighted, that for VSEPR, we treat double bonds equal to single bonds. So we still say around each of these carbons, they're the same as each other, but around each carbon there are 3 electron domains, 1 single bond, 1 single bond, 1 double bond, but they kind of work, they appear to act very similar to a single bond, and no lone pairs, so we say 3 electron domains around that carbon, same around that one. So the bond angles around those carbons is 120 and the trigonal planar. Okay, draw it around whichever one we want to. Okay, so they're both the carbons in that molecule trigonal planar. Yeah. Does that answer your question? Yeah, good. Yeah, so if you get a big molecule, we could identify any internal molecule of that, any internal atom of that molecule, and talk about its shape using exactly this theory. You obviously can't talk about shape with terminal atoms because they're just on the end going on their own. They can't have a shape as such. All right. I'll give you another example of that, which is on the slides. So that bond angle there is 120 degrees for exactly the same reason. Yeah. So we drew this molecule, I think, as one of our extension questions last week. So that's also trigonal planar. For all the same reasons that I'm not justifying on this occasion. All right. I want to do a couple more before we go. So I'm going to move on, if that's all right. So let's go back to beryllium. So 2 electron domains now. And the example you saw at the start of the lesson, the end of sort of what was lesson 3 in the sequence, you learnt the beryllium dichloride has that Lewis structure. And you just go through the process again exactly as before and say, how many bonding domains there? Show me with fingers, please, folks. Show me with fingers. How many? But you're gonna help me a little bit now. How many bonding domains around the beryllium, around the central atom? Everyone's going to show me with fingers. Everybody. How many bonding domains around that beryllium? Everybody, please. Good. So 2 electron domains. Right. Perhaps the tougher question then: how many lone pairs or non-bonding domains around beryllium, please? Show me with fingers. All of you, without exception. Some people are saying there are lone pairs, but there are none. There are no lone pairs. There's 2 bonds, no lone pairs. Beryllium had 2 in its outer shell. It can make 2 bonds. Doesn't obey the octet rule. So in total, you've got 2. Oh, I messed this up, haven't I? I should have said here 2 bonding domains. I'm sorry. 2 bonding domains, 0 lone pairs, and so there's 2 electron domains. Right? And then the shape is simply as shown. Really, I don't need to draw it again. The shape simply is linear, which is 180 degrees. And again, whenever you're justifying the electron domain geometry, please say max separation, minimum repulsion, and move to positions where the repulsion is limited. One of those 2 things. Either they get to positions of maximum separation, they get as far away from each other as they can, just like my arms either side of my body right now, or minimum repulsion, so they're not repelling each other because they're miles away from each other. So they go in this linear electron geometry, and the molecular geometry, because there's no lone pairs, is exactly the same. There's not many examples of these. It's beryllium really all the way, but there's one other example I want you to know as well, which you see, and you'll see more of this next year. But something like this. Do you know what we call this molecule? Anyone seen this before? Anyone at the back of the room? What do we call this molecule here? Seen it before? Okay, cool.
Ethine?
Yeah, so this is eth because it's got 2 carbons. If you've got a double bond, it's ethene, isn't it? But triple bond is ethyne. So this is ethyne. So I'll write that again so you can read it. And it's YNE, ethyne, C2H2. I think you drew it when we were doing our Lewis structures last lesson, so you have seen it before, but maybe you didn't know it was called ethyne. And this again, if we go through the process, show me please with fingers how many bonding domains there are around each of the carbons, around that carbon. How many bonding domains, please? Show me with fingers, please. Treating triple bonds like single bonds, like double bonds. Everyone's saying 2, which is encouraging. And how many lone pairs around that carbon, please? Good. So good. So 2 bonding domains, 0 lone pairs, 2 electron domains, linear, etc. Forgive me, but I'm not going to write it all out again. Okay. Did ammonia, done that one, done that one, done that one, done that one. Can you go back to the water and just also say on it, sometimes called V-shaped. You might see V-shaped there as well. So V-shaped is another way of, so just in case you see that in any videos or slides you look at, you've seen non-linear, bent and V-shaped, all of which will get you the mark in the exam. Right, I'm going to stop the video there, and what we're going to do, I'm going to give you a chance to look at some other ones. You can try and guess to work out what the electron domain geometry is. So there we are, that'll do.